Hey everyone, and welcome. Today, we're going to pull back the curtain on the very heart of your computer, the central processing unit. You know, the CPU? Think of this as a special guide for teachers and educators, all based on the fantastic research of Dr. Sudheendra S G. Our goal? To give you a really clear, simple understanding of the brain that makes all our digital tools tick. So here's our game plan. First, we'll talk about what the CPU's main job really is. Then, we'll peek inside at its most important parts. After that, we'll follow one single instruction on its journey. And then, we'll watch a whole mini program run step by step. Finally, we'll learn about the CPU's heartbeat and wrap it all up. Sound good? Let's dive in. Okay, so what is a CPU actually doing all day long? You know, its fundamental job is surprisingly simple, but it is the absolute foundation for every single complex thing that happens on your screen. Think of it like this. A program is really just a long to-do list for the computer. That list sits in the computer's memory, which we call RAM. The CPU, well, the CPU is the engine. It's the worker that pulls an item from that list, one by one, figures out what it means, and then makes it happen. It's the crucial middleman between the code and, actually getting stuff done. And this whole process is a constant, non-stop cycle. The CPU will fetch an instruction, then it will decode it to figure out the command, and finally it will execute it. And it doesn't just do this once. Get this. It repeats this cycle billions of times every single second. This little three-step dance, fetch, decode, execute, is the true heartbeat of all computing. So how in the world does the CPU pull off this constant three-step dance? Well, to make it happen, it relies on a super specialized internal team of three critical components. Let's meet them. First up, you have the registers. Now, if RAM is like the computer's main library, think of registers as the sticky notes right there on the CPU's desk. They're these tiny but incredibly blindingly fast storage spots that hold the exact piece of data the CPU is working with right this second. Next up is the ALU, which stands for the Arithmetic and Logic Unit. This is the real math whiz of the operation. Anytime an instruction says to add something, subtract something, or make a comparison like, is this bigger than that? The ALU is the part that does all that heavy lifting. It's the calculator. And finally, we've got the control unit. And this is the boss. If the registers hold the data and the ALU does the math, the control unit is the conductor of the whole orchestra. It reads the instructions and tells all the other parts, the registers, the ALU, the memory, exactly what to do and when to do it. It directs the entire fetch, decode, execute show. So we know the CPU follows instructions, but what does an instruction actually look like to a machine? I mean, it's not reading English, right? It's all just ones and zeros, binary. At its core, every single instruction is a simple two-part command. First, you have the opcode. That tells the CPU what to do, like load, add, or store. Then you have the operands. They provide the details, like what data to use or where in memory to find it. Now, to keep this whole process running like a well-oiled machine, the CPU uses two very special registers. First is the program counter. Think of it like a bookmark. It's always pointing to the spot in memory where the next instruction lives. Meanwhile, the instruction register is holding the current instruction, the one being worked on right now. Okay, this is where it all comes together. Theory is great, but let's see it in action. We're going to walk through a tiny 4-line program and watch every single component we've talked about do its job. This is where it gets real. All right, here's our setup. We've got our 4 program instructions loaded into RAM at addresses 0 through 3. And way down at addresses 14 and 15, we've stored some data, the numbers 3 and 14. You can see our main registers, A and B, are empty. And our program counter, our little bookmark, is set to 0, ready to point to that very first instruction. Okay, first step is fetch. The program counter says, hey, look at address 0. So the control unit goes to RAM address 0, grabs that binary instruction, and copies it into the special instruction register. Easy enough? Now, for the decode and execute parts. The control unit looks at the instruction and figures out it means load into register A the data from memory address 14. So it does exactly that. It zips over to RAM address 14, grabs the value, which is 3, and pops it right into register A. And once that's done, the program counter automatically clicks up to 1, getting ready for the next cycle. And the cycle just repeats itself. The program counter is now pointing to address 1, so the CPU fetches that instruction. It decodes it and sees another load command. This time it's put the value from address 15 into register B. So, in a flash, the number 14 is loaded into register B, and the program counter ticks up to 2. See the pattern? Now this next step is really cool because the ALU finally gets to jump in and do some work. The CPU fetches the instruction at address 2 and decodes it as add. So the control unit grabs the value from register A, which is 3, and the value from register B, which is 14, and sends them both over to the ALU. The ALU does its thing, adds them up, gets 17, and sends that result back. The control unit then writes that 17 back into register A. And, of course, the PC increments to 3. And for our last step, the grand finale, the CPU fetches from address 3. It decodes the instruction, store the value from register A into memory address 13. So the control unit takes that result, 17, from register A and writes it into RAM at address 13 to save it. And just like that, our program is done. We loaded 2 numbers, added them, and saved the result. That's computing. So we saw the CPU move through those steps one after another. But what's keeping the beat? What's telling it when to go from fetch to decode and from decode to execute? Well, that's the job of something called the system clock. You can think of the clock as a tiny, incredibly fast metronome. With every single tick, the CPU does one tiny little thing. And the speed of that clock, it's just exploded over the years. The very first microprocessor back in 1971 ran at thousands of ticks per second. By the 90s, we were at millions. Today, we measure it in gigahertz. That's billions of cycles every single second. It's just wild. And what's interesting is that this speed can actually be changed. You might have heard of overclocking. That's when tech enthusiasts force the metronome to tick even faster to squeeze out more performance, but it generates a ton of heat. On the flip side, your laptop or phone does the opposite. It underclocks its CPU, slowing the tick way down when you're not doing much, just to save power and make the battery last longer. Okay, we've seen all the pieces, and we've watched them work together. Now, let's just take a step back and put it all in perspective to see what this really means. Here's the truly amazing part. The entire, complex, rich world of modern software is built on this ridiculously simple and fast foundation. At the very heart of it all is that constant loop. Fetch, decode, execute. It all happens with registers as the little workspace, the ALU as the calculator, and the control unit as the director, all marching to the lightning-fast beat of this system clock.
And that right there is the core magic of computing. Just think about it for a second. Every single thing you do on a computer, from a simple mouse click to streaming a movie, is just that machine breaking the task down into millions or even billions of these simple fetch, decode, and execute steps. So the real question to leave you with is this. How do these incredibly basic, almost primitive steps stack on top of each other to create the infinitely complex and amazing digital worlds that we all live in every day?